Hello everyone, and welcome to our system demo for cyber defense using Pretense and SDX-Driven cloud platforms. My name is Travis, and I was part of a great team which implemented this system for Dr. Callion's Cloud Computing 1 course at the University of Missouri-Columbia. Our hope with this presentation is that you find this project interesting and gain an understanding of the power of software-defined exchanges, or SDX, and open-source software-defined networks. So I'm going to speak on a number of topics today. First, we're going to start with defining what we're doing and why is it useful. We're going to talk a little bit about and describe the different tools and software we're using. I'm going to show you several diagrams and also describe how our systems work. You'll see the layout of our test bed, understand how we've moved a switch closer to the attacker, and how this, alongside a software-defined network, helps defend against loss of availability attacks such as DDoS attacks. Then we're going to jump into the exciting stuff, a demo of our admin UI, Frenetic, our OpenFlow controller, and how we use these tools and software to control the flow of data on the network. You'll also see how easy our admin UI makes it for an administrator to make quick dynamic changes to the network on the fly. You'll also see when an attack occurs on the network, how it can be identified, and how a policy update can quickly be put into place, rerouting the attacker traffic away from the core infrastructure and allowing users to continue using services without disruption. Finally, we're going to go over how we evaluate performance of the system, the engineering trade-offs and costs, as well as our conclusions and planned future work. So what are we doing? Well, we're developing a cybersecurity defense system which will help prevent against loss of availability. We're rerouting attacker traffic in such a way that they are isolated from the rest of the system while at the same time under the pretense that their attack is successful and that services have been disrupted, creating the said loss of availability. This is accomplished with OpenFlow controller and software-defined networks, which can reroute attacker traffic closer to the attacker. We provide interfaces for controlling dynamic changes in the network via our admin UI. Administrators can monitor network bandwidth and apply network policy updates dynamically. They can monitor the network and servers and make decisions as needed about how to change the data flow of the network. And all in all, this provides a better user experience. So why is this useful? Well, our core infrastructure will remain untouched by attacker traffic. We can prevent attacks before they impact those important services and servers. And we can fool the attacker into thinking that their attack was actually successful, while regular users can pretty much keep on using the system without interference. So the core logic of our system is that we control the network dynamically and on the fly. When an attack occurs, it can be mitigated immediately and with ease. So, our tools and software. Our admin UI is a custom interface built for administration of the SDX network. It provides total network as well as per switch, per port, and bandwidth, graphs, and information. It also allows for an administrator to push policy updates to the network, be it the network as a whole, individual switches, or even individual ports. We use MySQL for sorting and storing data, information about the data transmitted on the network. We store per switch data on packets transmitted and received, as well as bytes transmitted and received. Those are pretty much our two most important statistics. But we also store data on packets attempted to be received or transmitted but were dropped, number of packets that erred upon receipt or transmit, the number of packets with frame errors, and number of packets with buffer overrun errors. So Frenetic is our OpenFlow controller and the true brain of the system. This is also commonly referred to as Universal Resource Broker, or URB. It controls any switch running Open vSwitch and connected to the controller. As long as the switch is routable to a controller, a switch can even be in different domains or cloud services. As long as it's routable, you can control it. So the Frenetic runs on the controller itself, and we're going to update policies to it via RESTful web services. And the policy updates can be for the entire network, or they can be for multiple domains, single or multiple switches, or even multiple ports on a single switch. So Frenetic also allows for Python scripts to control the network flow and push data packets to the database. So we're going to be running several Python scripts to kind of monitor those statistics. And finally, we're going to be using Scapy, which allows us to create, rewrite, and send packets wherever we want. We're going to be using this to create fake packets, which look legitimate, to be sent back to the attacker in hopes of fooling them into thinking that they're actually hitting the real server and services. So, just a quick logical diagram of our base system. So we start with the controller, and the controller is making all the decisions about where data flows on the network. And on top of the controller sits the admin UI and MySQL database. Like I said, the admin UI allows for administrators to quickly and easily monitor network bandwidth and utilization. The MySQL database stores information about what's being transmitted over the network. For the database itself, it was placed on the controller for ease of implementation, but it could also reside on its own system. So on top of that, we have Frenetic, the OpenFlow controller. It sits on top of the controller itself, and it's the interface between the controller and each switch on the network. So network policies are generated within the admin UI and applied via Frenetic, and those are pushed out to each switch routable on any domain. Now, each switch and the domains have quarantined systems attached to them. And basically, these quarantine systems are the ones running Scapy, and they're going to imitate the server, which is under attack, and responding appropriately. And so all the users are sitting on top of those switches and connected to those. So as you can kind of see from the complete diagram, each switch on the network forms its own barrier against DDoS attacks, which are connected to it. It's kind of a distributed defense against a distributed attack. Alright, so I'm going to run through a quick breakdown of how data flows through the software-defined exchange, and we'll see all of this in action shortly. So you have a user that connects to one of the slave switches, and data from that passes to the root switch, and from the root switch it passes on to one of the servers. So that's basically how a normal user would connect to a service. Now an attacker comes in and they start sending data through the slave switch. Alright, so we identify that, and that data is then redirected to the QVM, and it actually never reaches the root switch or the core infrastructure and servers. The attacker traffic is redirected. The QVM responds to the attacker like it is the server, fooling the attacker. And the user data path is to the server isn't congested. It provides a better overall user experience, and we only allow legitimate traffic to actually pass to the servers in the first place. It keeps user interruption kept to a minimum. Alright, so now a quick overview of our test bed. So we designed and created this in Genie, and we start with just our controller, the brain of the system, and it's just a single machine. It's not internally connected to anything else in the system. And within that we have the root switch with 3 separate servers that forms the core infrastructure. And then at the edge of our network we have a slave switch, 2 users, 3 attackers, and 1 quarantined VM. So pretty much what we're going to be seeing in our demo here in a moment is that we're going to have an attack coming from this attacker 1 right here, and it's going to come to the slave switch, and initially we're going to be able to hit the server 1 over here because we're leaving that traffic open. And I'm going to show you how on the controller over here through our admin UI we can push a policy update that will then begin rerouting that traffic from attacker 1 down here to the QVM. And the QVM is going to respond in the same way as server 1 responds. Alright, so I actually just went over that, so we'll keep on going. Alright, so for our demo, alright, here is our admin UI, and we have bandwidth utilization graphs. This is an overall for the entire network. We have one for the root switch, one for the slave switch, and we have packet logs that are coming in. Now, none of this stuff is running just yet, but we're going to get into that. We also have an area for blacklisted IPs, so this will show you IP addresses, MAC addresses, and timestamp of when we identified an attack was going on and blocked that. So this data gets updated by the QVM system whenever it starts responding to an attacker. And under settings here, these are our options that we have to change policy updates. So you can pretty much, what we've done so far is just hard-coded in some different policy updates. These are all JSON files that describe how data is going to flow throughout the network. So we have one for opening all connections, redirecting attacker 1, attacker 2, attacker 3, redirect all 3 attackers, and then block all connections on the system. Alright, so that's pretty much what we're going to be looking at here in the admin UI. Now, let's go ahead and start up Frenetic, and you can get an idea of what it looks like. Alright, so this is going to pull up our open flow tables right in here. So we have 2 switches. Each of them is listed here with its own open flow table showing you how traffic is being rerouted. And right now, no traffic is being rerouted. So if I were to go down to attacker 1 down here and try to ping server 1, and if I were to try to ping server 2 from server 1 over here, you're going to see that none of these pings are actually going to get through. Everything's going to be unreachable. So we'll leave these going for a second here. Now what I'm going to do here is I'm going to go ahead and I'm going to start up statistics. So we have 2 separate Python scripts that run stats for the root switch as well as the slave switch here. Alright, and so this is info about the statistics being gathered on the network. And we're going to go ahead and click here and go ahead and open up all our connections. So we're going to submit the new policy. And you'll see that the open flow tables have both been updated. Here's our slave switch allowing data to flow between port 1 and the remaining 6 ports, 2 through 7. And same on our root switch here between all the servers. And you can see down here that all the pings have started to go through. So attacker 1 is able to reach server 1, and server 1 is able to reach server 2. So if I were to go here and check our bandwidth utilization, you'll see that this is now flowing. So it updates every couple seconds. You can kind of see we have sort of a generic ping graph going on here where it goes up and down, up and down, up and down. And same thing, you can see stuff passing through on the slave as well as the root switch. So I'm going to go back to our settings real quickly. I'm going to block attacker 1. Now, this is actually going to redirect everything from attacker 1 to the QVM, but we aren't actually running a real attack yet. I'm just going to show you how attacker 1 will actually stop pinging here. So we get a new policy update, and you can see port 6 right here is actually our attacker, and we're only allowing the attacker to go to port 5, which is the quarantine system. And so the quarantine system is not set up to respond to anything just yet, but you can see that the attacker's pings have actually stopped. Whereas the server over here, the server's still going just fine because we haven't blocked anything there. I can go back and I can open up all the connections again. And the pings start up again over here on attacker 1. We're still good over here on server 1. And I can go in here and I can block all connections. And this is going to stop both of them, so we aren't allowing anything through. And I can open up all connections again. And they'll both start up again. So you can kind of see, get an idea of what this is doing, and actually, yeah, our bandwidth graphs are still going. And we have no blacklisted IPs yet. Alright, so let's go ahead and we'll try running an attack, and I'll show you how this works. Alright, so we have everything open in our open flow tables here. I'll go ahead and close this, and let's see. We're going to go ahead and run the attack. Alright, so this right now, with everything open, we have, basically this is just pinging. It's using Scapy to ping the server one over here. And we can see this happening over here in the root and slave switches. There's traffic going through. So let's say that we see this as an attack going on the network. What we can actually do is we'll go in here and we will redirect the attacker. Alright, so now this is going to look like the service went down. Basically, the server stopped responding to the pings. So now what we're going to do is we're going to run the defend. Is it called defend? Let me see. Yeah. Alright, so we've started this up on the QVM. Alt attacker traffic's being redirected to the QVM. So now, if the attacker were to try to send off another attack, we can see it's actually being picked up by the QVM here and responded to. And we can see that the traffic on the route has actually totally dropped off because we're not allowing that traffic to go to the route anymore. We aren't allowing those pings. And all of that is actually happening on the slave switch over here. Now what's going to happen right here in our script on the QVM is that the QVM is actually set up to only send out packets for a random time between like 20 and 40 seconds, at which point it's going to start failing, and the attacker will think that they've brought down the service again. When in reality, none of that traffic is actually getting through whatsoever. And so back here in our blacklisted IPs, you can actually see that we've picked up the IP address and the MAC address, and it was added just a few minutes ago. So now we can keep a history of this and who has performed these sort of attacks. And you can actually go in, and if you wanted to write more complicated policy updates, JSON policy updates, you could build these. And actually, let me, I don't have them available right now, but you could build some other ones based upon like MAC address, or right now you can actually see it here. We're redirecting based upon port numbers. So that's just the port that on the switch that the users or the attacker is connected to. You could build these based upon MAC address. You can build them based upon IP address and do rerouting. You have a lot of different options for rerouting. So, let's see, minimize this. So I'm going to go ahead and show you one last diagram, kind of detailing what we just saw in action. So you have the attacker who sends the attack. It hits the switches. All right, with the help of the admin UI and Frenetic, this data gets sent into the database, we display it, and we detect the attack occurring. All right, so we use the admin UI to send policy update to Frenetic, which then sends the updates into the switches. The attacker then gets redirected to the quarantine system. The server begins to no longer be impacted, and we start responding as though we are actually the server. And the attacker can continue doing that as long as they want. We don't really care what happens to the quarantine system. Um, what really matters is that services are no longer disrupted for users. All right, so I'm going to go over a couple of the trade-offs and costs. So hopefully you'll easily see that there's going to be additional costs because you're running these quarantine systems on the switches, or closer to the switches, closer to the attackers. And you may need to run one or more depending on how many attackers you're having. So you could potentially spawn up multiples and redirect to additional quarantine systems if necessary. However, I think these cost savings can be quickly realized whenever you see that users are no longer going to be impacted by these attacks. They can continue to use your services, they can continue to spend money, and they're not going to know anything's going on, which is really for the best. Right, your core servers and protected from attacks. So this helps to protect, sensitive data that might be on there. If there are existing flaws in your core infrastructure, this can help to prevent them from being exploited. It protects your investment. It protects your users, especially if you have potentially sensitive data that could end up getting access somehow on those servers. And the last thing is, you're going to need someone who has quite a bit of knowledge about software-defined network, software-defined exchange, OpenFlow, Frenetic. So you need strong support there as well. All right, so for our measurements of success, we're basically having network data utilization graphs that monitor all the different traffic coming across the switches so that an administrator can make knowledgeable decisions about how to control the flow of the network. We want to be able to, blacklist the IPs and show where the attacks have come from before, so that it can be used in the future. And we also want attacker traffic successfully rerouted and held in a state of pretense. All right, so hopefully with all the details we've provided up to this point, you can begin to see how easily this sort of thing can scale out to multiple switches on the network and cover more and more users, and how this can be used to prevent attacks on the network and control the data flow closer to the attackers and the users. So other future ideas that we'd like to see implemented at some point would be expanding the network to house many more switches, including switches on different cloud systems, like going between Genie and AWS or other services. Another idea would be add a load balancer to the controller, because the controller could be a potential point of vulnerability, and you'd like to make sure that if a failure does occur, it doesn't bring down your entire network. We also think it would be interesting to build a new UI on top of the admin UI, which allows administrators to visually build out network policies. Perhaps like a way that they could drag and drop different portions of the network, rearranging the network flow on the fly, and having the JSON policies built and applied automatically in the background. Because right now, it's kind of difficult to build out those JSON files. There's just a lot of data in there. I think having something to allow the admin to visualize all that could really help building complicated help in building complicated policies. And a final idea would be to implement additional false reality techniques. So there's currently situations, I'm sure, where this sort of the sort of presented defense mechanisms you've seen here today could also be defeated. And at times like that, you would also want additional defenses in place that would kick in, such as like an invisible user migration, where if if a server were compromised, you can actually redirect user traffic to a different unaffected server while the attacker traffic is still hitting the original server. So in closing, we'd like to thank you for listening to our presentation. We hope that you enjoyed it and that you can take some of these techniques to implement in your own systems. Thank you.